And off we go. We're recording. Okay, so here's where we were last time. We made several arguments kind of addressing similar questions, and just as a quick summary, we started off with the volume question. How do you compute volume? We came up with an iterated integral that you then crank with the fundamental theorem. That was our first thing. What we found, though, is that you can't really make arguments like this. It just doesn't fit. The units just don't work. It doesn't make any sense. Right? We also have previously noted that you can't just immediately claim mass to equal to volume. What? Where does that come from? Right? There's no argument without a Riemann sum. And since we're going to be eventually doing a Riemann sum anyway, we don't need such a non-existent argument. Okay, the next thing we did is we came up with this idea of a double integral, namely a two-index Riemann sum. And the idea was that whether you're computing volume or you're computing the answer to other applications, as long as the whole is the sum of the parts, pretty much, that construction's going to allow you to at least write down an answer to any such question. Okay. All right, and then lastly, we noticed on this picture, and this is about where we ended last time, we noticed that, oh my gosh, check it out. Now I have two different methods, two different expressions that answer the same question, namely how to compute volume. And when you have two answers to the same question, those things must be equal. And that allows you to turn double integrals into iterated integrals. Right, so that leaves our diagram looking like this. And again, just for emphasis, the red, it means no-go, right? So I'm going to erase those now that, So this is basically what we have. And now you can see the path, for the way we're going to make arguments. You know, if we have some question of how to compute something, some quantity, some accumulating quantity, so the whole is the sum of the parts. You can chop it into pieces and add up the pieces, that kind of thing. Step 1, write it as a double integral. Step 2, turn that double integral into an iterated integral. Step 3, plug and chug with the fundamental theorem. And this is where we're going to pick up and actually do one just like this. Okay. Does everybody remember all of these? Again, that's a lot of ideas, right, that we're kind of briefly summarizing here. Okay, so here we go. Question. We want to compute the amount of mass distributed over this rectangular sheet. So there's a certain amount of mass distributed like this, but with non-constant density. And so I'm going to try to represent that it's more dense the closer you get down to the sort of bottom right-hand corner. And so what am I going to do about this? Well, you can't use a single variable calculus approach to this problem, but what you can do pretty immediately is say, look, we know how mass works. We understand the nature of mass, and the whole is the sum of the parts. Right? We also understand about mass that, let's see here, let me get rid of all the... in fact, I don't really need that. We also understand that for any given little piece of mass, if I'm interested in just this one little piece right there, how much mass is there in that one little sub-rectangle? Well, mass is mass per unit area times area. I mean, this is the whole point of the concept of mass per unit area, is that you can multiply it by area to get mass. That's its job, right? So not a big leap there. Okay. And then finally, we'll observe, oh my gosh, look at this, check it out. That's exactly the definition of a double integral. It's a two-index Riemann sum. That's what a double integral is. Okay, so we have done step 1 up here. Then we have now successfully turned, let me get rid of all of this, we have turned a mass question into a double integral. Everybody on board? Everybody happy? Okay. I'm going to come back and talk about this alternate notation in a minute. For the moment, I want to just get a win into the win column. The second step is to argue that, hey, good news, double integrals are iterated integrals. Now, we've already made the argument as to why. I don't have to prove it every single time I use this point, right? Double integral is an iterated integral, so cool. This double iterated integral that I had, I'm going to rewrite that as the iterated integral. Notice that the range of values for x is indeed the given range of values of x, and further notice that the range of values for y is indeed the given range of values of y. Okay. Yeah? Yeah.
If density is non-constant, wouldn't the density inside that square also be non-constant?
Yes, that is a valid point. So this is analogous to, that's a great question. Let me address that by reminding you of a single variable calculus scenario that I'm sure you've digested, right? So why can't we just compute this by calling it a rectangle and the height times width? Well, because the height isn't constant, right? So we cut it into strips. I know you've seen this a million times, right? We're going to cut this into little strips like this. And on these little strips, bad news, the height is still not constant, but it's close, right? And we can, if you wanted to get all formal and rigorous and careful about this, right, then we would argue about, given continuity and blah, blah, how we can argue that the errors go away, right? And so let's not, right? But morally, it's the same point. On sub-intervals in this case, the error is going to be small, and in the limit, the total error even will just be small. So exactly the same point holds for here we go. For this scenario, yes, you're right. There is going to be a certain amount of error on here, and it's okay. It's going to, in the limit, go away in the end.
Okay.
Yeah. All right. Okay. So lastly, well, we have a iterated integral. How do we compute iterated integrals? Well, we plug and chug with the fundamental theorem, and that gives us an answer, and we've already seen how to do that. Okay. All right, so that's the process, three-step process. Again, exactly what we have here, right? So first, make a double integral. Second, rewrite it as an iterated integral. Third, compute with the fundamental theorem. Okay, now let's talk about this notation down here. We've talked about the definition of an integral, and it's just notation. It's not like integrals are pre-existing things that we then noticed were equal to Riemann sums. This is literally the definition of an integral. And so since this is just notation, people do tend to be a little sort of a little casual about certain aspects of it. In particular, even though we don't really have a separate definition for dA, it's nice to just think of dA as being delta x times delta y. Right, why not? And likewise, this notation here, in the absence of a complete Riemann sum, we haven't really defined that as a thing, but it's very convenient to use this as just an expression representing, look, I'm adding up a bunch of these things in the limit as the slices get smaller and smaller. So with that in mind, this expression right here, well, we can just rewrite it like this. Why not? In some sense, we're on our way toward writing it in integral notation anyway, so why not just go ahead and adopt this very convenient integral notation along the way? Where's the harm? Right? So anyway, this kind of notation here, so you see is sort of an alternative development getting me to a double integral, same double integral that I got the other way, right? This shorthanding of the notation is nice, right? It's pretty common, and so you're going to see stuff like this, and it's fine. It's understood. And by the way, very convenient, especially in an example I'm about to show you in a minute. Okay, so, all right, now one last thing I want to say about how to write down answers to questions like this. Y'all will recall, this is not a class about answers. It's a class about ideas and reasoning, right? I know I say that a lot. I say it a lot because it's important, right? So if what you were interested in were the answer, which which it's not, but hypothetically, if it were, then there would be a case to be made that, look, I know that I am eventually going to be writing down an iterated integral. How about I just write that iterated integral down immediately? Why do I need to write down the double integral that's only purpose is to allow me to write down the iterated integral that I'm going to compute from? It seems silly, perhaps, to bother writing down the double integral. And I just want to point out, if you're only interested in the answer, then yeah, that's true. But keep in mind, that is absolutely not the only thing we're interested in. We're interested in arguments, mathematical arguments, right? And as a mathematical argument, we've already agreed that that is sketchy. Right? There's real problems in trying to make arguments like that without double integrals. So I don't think this is a good plan. I think that an argument like this, even if you knew in your head that a double integral was inside of sort of the first half of that argument, from what's written on the paper, this is indistinguishable from someone who's making just a straight up invalid argument. Right? So this is not allowed in this class, and I expect to see double integrals written down, just as if only to recognize that we're making this valid argument. Now, so that's the bad news. Here's the good news. It's super easy to write down the double integral, right? All you have to do is instead, let me do this in red to show that this is not okay. Instead of immediately writing down that, no big deal. Just give me that right there. Look how short it is. It's nothing to it, right? That's it's an easy thing to do, and further good news. Not only is it easy to do, it's worth points. Right? So on a question, for example, where you're like, oh my gosh, I really don't know where to go with this. What am I going to do with this question? How do you write down iterated integrals anyway? Just merely having written this will be worth a little bit. I mean, maybe not a lot, but a little bit. And so think of it as free points. Right? Glass is half full, not half empty. Right? Okay. All right. Okay. All right. So this next example is just to show the value and the convenience of this integral shorthand for representing Riemann sums, but it's also just a nice example in general. So here we go. Let's suppose we're building a wall, stone wall. I visualized this example when I was we were building the house that we currently live in, and there's a sort of a stone facade that's slightly larger than what I have written here, but about this. So the idea is it's going to take a certain amount of work to build this stone wall. In particular, there's a bunch of chunks of stone that are sitting here at ground level. Bunch of chunks of stone. Each one of those chunks of stone is going to have to be lifted, right? This chunk of stone sitting right there is going to have to be lifted a height y to get to where it's going to go in the wall, wherever that ends up being. Yeah. Okay, so that takes work. What's the grand total amount of work involved here? Further complicating matters is that the density of this wall, in other words, how much stone mass, how much stone weight per unit area is there at different locations on the wall. And let's see here, it appears from what I have written down here that it gets just from, and this isn't how the wall actually is. This would be a weird looking wall, but it gets more and more dense the further you go sort of up and to the right, which shows up better in blue, I think. So how do you factor that into the calculation, right? So here's the argument, and the big idea is, first, I observe that the whole is the sum of the parts. Now, technically you don't have to write that down, right? As I've discussed before, it's fine to just immediately write down this double integral. The problem is in this case, while it happened to be easy to immediately see what the double integral was, it's not immediately clear what the double integral ought to be for this question. How do you write that down, right? So I'd like to slowly develop my double integral using integral shorthand, because each little step along the way is a relatively easy argument. So I start off with the very easy argument that the whole is the sum of the parts. If I can figure out how much work it takes to pick up each specific little stone, and then just add up over all the stones, surely the total amount of work is the sum of those individual pieces of work, right? Everybody buys it? Okay. All right, so let's talk about that specific piece of stone. This little piece of stone right here. And I'm going to remind you, work is force times distance. High school notion of work. I don't even have to think about this in terms of dot products. Because the height that it goes up, how much does it have to get lifted? Well, that's literally the y-coordinate of that point. And any horizontal aspect of it, I just ignore. No problem. Okay. All right, now, of course, this is what we call a differential amount of work. I mean, how much work is this? Well, this amount of work is, that's a small part of a large total, right? And, well, likewise, notice that this is a differential amount of weight. And just as a quick reminder, if you haven't had a physics class or if it's been a while, what have you, weight is just a notion of force. So I'm using F to represent weight because weight is literally a force. Okay. Right. So this also is a differential amount of weight because there is an entire weight of the whole wall, but we're only talking about the weight here of that one little piece of the wall. Okay. Okay, so this boils down to looking at this little piece. Work is force times distance. And then I make a sort of an analogous observation here that weight is weight per unit area times area. And I was given weight per unit area in the form of, that's how we describe a density. How are we doing? Is everybody happy? Yeah.
So here this density, the number density is down to mass.
Yeah. That's right. But I mean, one of the things we're going to be doing in this course, by the way, is sort of broadening our notion of what the word density means. And you've already kind of noticed that I'm not using it exclusively in the sense of mass per unit volume, right? I'm doing this weird thing where it's mass per unit area. But in general, you can broaden the idea of density as mass per unit any sort of size. And you just have to ask yourself, how are you imagining the mass distributed? Right, so just as an example, right? If you go to the hardware store and buy chain, and you ask, you need to get some sense for how much the chain weighs, how heavy is this chain? They will tell you about its mass per unit length. Even though it's not one-dimensional chain, the point is you imagine it as the role that it serves is to span a distance, and so it behaves, we treat it as if it's one-dimensional because that's its job. That's how we're choosing to visualize it. So any notion of size can be used for density. Is that cool? Yeah. Likewise, any notion of stuff. It doesn't have to be mass. So as you pointed out, in this example, we're talking about weight instead of mass. That's a different kind of stuff. You can also talk about population density. Right? That's a different kind of stuff than mass. And take your pick, anything else. And we're going to broaden it even further a little bit later in the course, but not right now. So that's just foreshadowing. Okay, all right. So notice how I've used this very convenient shorthand of talking about little differentials. This represents a differential small amount of area out of a whole amount of area, and this is a small amount of weight out of a whole amount of weight, and this is a small amount of work out of a total whole amount of work, etc. And it just makes for this really nice convenient, streamlined argument that eventually, as you'll notice here, gets me down to a double integral. Hard to see it coming in advance, that this should be your integrand. You can't just immediately write that down. It's not clear. So it's nice to have a way to develop it. Okay. All right, and everything in the rest of this example is, that's just details that, double integrals or iterated integrals, blah, blah, blah. Okay. All right. So now we have to move on to a weird question. That is, what if the whole that we want to break up into parts is not a rectangle? By the way, welcome to the real world, right? What are the odds? What are the odds that the question that I'm going to need to deal with is just happens to be a rectangle? Seems unlikely. Not that it won't happen, but in general, you wouldn't expect domains to be rectangles. So, for example, if I have a shape like this in the xy plane, not a rectangle, and I'm looking at some surface, and if I want to compute the volume sitting under some surface over this non-rectangular domain, how do we compute that volume? Well, you'd be surprised. I mean, pretty much everything we've done with rectangles applies to not rectangles also. It's just wonderfully convenient, as it turns out. So in particular, I can take this volume and I can slice it up like so. Those slices I can view as being thicknesses, little dy's, right, that I'm going to multiply by areas. And let's see if I can get this well done here. Okay, so little cross-sectional areas. Area times thickness gives you volume. That cross-sectional area is still the area under a curve. Areas under curves, more to the point, areas under graphs, still integrals. Just now integrals in the, you'll notice, the x direction. Everything works, pretty much. Everybody see how much this is? We're doing morally equivalently exactly the same thing, right? There is one little detail that isn't quite the same, and this is really the only thing you have to keep track of when you're talking about non-rectangular domains, and I just need to zoom for, here we go. The one little detail is that I claim the bounds, the inner bounds, are not going to be constants. They're going to depend on y. And I claim you can just visibly see that in the picture. Let's suppose you're looking at, for example, this value of, let me switch to the pencil. You can take a look at this value of y right here. For that value of y, notice that my lower bound is going to be that value of x. But if I looked at a value of y over here, right, that's a different value of y. Well, then my lower bound for x, well, let's see, that's a confusing little point. Let me do it about like that. My lower bound for x is going to come from that point, which gives me a different value of x. So, if the value of the lower bound, if the x-coordinate, therefore, is dependent on y, that means it's a function of y, and that's why we represent the x lower bound as being a function of y. Everybody on board? That's the only difference. Everything else is pretty much the same. All right,
For rectangular, you could flip the integrals.
Correct. Not so anymore, and that's right. And you can almost already pretty much see why it is, right? Because if these inner bounds are going to be functions of the outside variable, then when you flipped them, you'd have the outer bounds being a function of the inside variable. It's not even, that doesn't make any sense. Yeah, absolutely. Yeah. Does that satisfy? Yeah, good. Right. Okay, so now even more good news. This argument that I just made here, about how to determine those inner bounds. Notice, in that argument, everything I did was happening in the XY plane, right? The verticality of this, how tall, how much up. That didn't have anything to do with the argument that I just made about the bounds. The vertical aspect of that picture only manifests itself in the integrand. That's what tells you the integrand, right? But everything that you need to see to determine those inner bounds, you can see by just drawing only the domain itself, right? I don't need to see what's going on with the integrand to understand the bounds. The bounds come exclusively from the domain. Does that everybody see how that is? Just the argument we made, it was literally all in the XY plane, right? So this is super valuable, partly because drawing three-dimensional pictures is a lot harder than drawing two-dimensional pictures. And we're actually going to later today extend the ideas that we're doing here to what we're going to eventually call triple integrals, for which we would need a four-dimensional picture. So that's a creepy idea. We'll get to that in a few minutes. But that's really hard in the sense that you can't do it. You just flat cannot do it. Okay. All right. So it's very valuable to be able to recognize what I'm going to call a dimensional convenience, right? Being able to take something that you were dealing with on a three-dimensional picture and reconceive of it on a two-dimensional picture. Big time value. So I want to go through that little argument again now. It's the same exact argument, but in the context of this now three-dimensional picture. And so, okay, for a given value of y, that y identifies a certain point that's going to give me my lower bound. That point has an x coordinate that tells you how that bound, right, that x lower bound is a function of y. And so roughly speaking, in order to make this happen, the way you're going to do it is you're going to recognize, look, if I need to find my lower bound, what's my lower bound? I identify the corresponding point. That point is going to be on some identifiable curve. That curve will have some equation. Obviously, we're going to have to do algebra at some point. And in that equation, all we're going to do is solve the equation, and that will give me my lower bound. Likewise for the upper bound, of course. Different curve, different equation, same process. Okay, so let's see that in action. Here we go. Okay, so on this question, we're interested in this double integral. Now, I want to emphasize one thing you're going to notice conspicuously absent from this example. I've given you no indication of why we're computing this double integral. Does this have something to do with mass? Are we computing volume? Are we computing the population of this little triangular whatever? Where did this come from? Right? And it doesn't matter for the purposes of this example. Just a quick reminder, what we're doing with all of this is we're doing business on this diagram here. And I'm just interested for the moment in addressing this question of how to turn a double integral into an iterated integral. That's all we're interested in for this purpose. So yeah, the integral we were given, yeah, of course, yeah, it came from some application. Yeah, fine, absolutely. But we don't need to worry about that for the moment. Okay, is that cool? Okay, yeah, here we go. All right, so notice my domain is a triangle specified by its vertices. So there's my triangle. Now I'm going to go through this process just like we did here. I'm going to compute lower bounds by identifying the relevant points, understanding those points as coming from certain curves, working out what the equations of those curves are, and then solving for what I need. And in action, here we go. Let's see here. So for a, let's see here, I'm slicing this the other way, it looks like. So we've got x going from 0 to 1. Right? And then we're going to focus one at a time on individual values of x. For that specific value of x there, let's see here, my lower bound for y comes from this point. Right? You imagine y sort of going like that. That point is on that curve, which has this equation. Actually, let me use a better color choice here. That point is on that curve with that equation. And now let's see, what am I doing here? I'm trying to solve for my lower y bound. So I need to solve for y in this equation. Good news, that's easy. Sometimes you get lucky. Solving for y in an equation that starts with y equals. Right? Gotta love it. And so, boom, there's my lower bound for y. And notice y being 0 is my lower bound for y. Everybody see the process? One important little side note I want to make here. The question before you is not, do you believe that the lower bound is 0? The question before you is, do you see the process by which I concluded that the lower bound is 0? Because while this one is a convenient, and sort of easy, sort of obvious kind of a thing, they won't always be, right? So my interest here is in this several, 4-step process. You've got to identify the relevant point, identify the relevant curve, identify the equation, solve for the relevant variable. That's what I need to make sure everybody's good with. Okay. All right, so let's talk upper bound. Again, we're talking about the same value of x. For that same value of x, y is going to do like that. Y will then end at that point, which is on that curve. By the way, how do I know it's that curve? The picture. Right? Pure geometric interpretation from the picture. I cannot emphasize enough, you need the picture. The picture is what tells you where the point is that you need to, identify. And you can't, it's not that you can't do this without a picture, but it's just really, really hard to make a meaningful argument without a picture. Right? So you got to have a good picture. And again, if you have the point of view of I've done this before or whatever, and I feel like I can get the right answers. Yeah, again, it's not about the answers; it's about the arguments. Right? So you got to give me an argument, independent of whether your answer is right, and way harder to make a valid, meaningful mathematical argument without the picture. Okay, so reminder: for a given value of x, there's that purple point gives us the upper bound for y. That purple point is on this blue curve. That blue curve, I got ahead of myself here. That point, the blue curve, has that equation. Reminder, what am I doing here? Why am I looking at that point? Why am I interested in this curve? Because I'm trying to solve for y to get my y upper bound. So in this equation, I need to find a formula for y in terms of x. And there it is. The formula for y is x. Is that cool? All right. Very importantly, by the way, it's not y. Right? It would be absolutely nonsensical to put y there instead of x. I need to know how y depends on x. I need its expression for how to compute it as a function of the outside variable, in this case x. So it's got to be x. Okay. All right, so that's the process, and now we're just going to basically do a bunch of examples just to make sure we've got the process here. First example I'm going to do is to consider the same domain. I'm just going to slice it in the other direction just to show we can. So here I'm going to do my y slicing on the outside, and so now for a given value of y, I'm going to try to understand what are the x bounds, right? What's this range of values of x for a given value of y? Okay, well, again, playing the game. Let's see here. This is the point that tells me my lower bound. That point is on that curve that has that equation. Quick reminder, because I get confused easily, I am looking for a formula for the x lower bound, so I need to solve for x. Solving for x, I get this formula for x as a function of the outside variable y. Cool? Notice I did that a little faster. We're going to have to speed up just to, the more examples we do, the more y'all see the process, the faster we can move. Analogously then, there's the upper bound. That points on that curve that has that equation. I'm solving for x, so we solve for x. That's a nice easy one as well, and the upper bound for x is 1. How we doing? Everybody good? Cool. All right. Here's another one. Let's see here. So I have two curves here. I have this parabola. I have this line. I'm looking for the region that's bounded by those two curves. Now I do need to stop and say a word about this language. When I say bounded by, this means two things. And you got to be careful with this kind of thing. Just a reminder, part of your job as students, right, is not only to answer the question correctly, but to interpret the question correctly in the first place. So when you see this language bounded by, that means two things. It means that the region I'm interested in, its boundary consists of these curves. That's part of what this means. The other part of what this means is that our region is bounded. Bounded means you can put it in a box. It means it doesn't extend infinitely in any direction. So this region here that I have highlighted in yellow, you can see is bounded because look, I just put it in a box. Right? Whereas, on the other hand, you might be tempted to look at the picture and think, well, look, there's a region up here whose boundary is the blue curve and the green curve. Why isn't that the region that's bounded by green and blue curves? Well, the answer is because it's not bounded. You cannot put that in a box. You can't draw a rectangle around that region. It extends infinitely. Everybody on board? Okay. All right. Okay, so how are we going to deal with this region? Okay, arbitrarily, I'm going to do my x slicing on the outside. I notice x goes from -2 to 2. Now let's talk, how did I come up with those bounds? This wasn't immediately clear from the statement of the question, but you will notice that this point that defines my lower bound, that points on a couple of curves. It's on this curve with that equation. It's on this curve with that equation. That point then is going to be a point that satisfies both equations, and I can just solve, and it gives me my -2. Almost. It actually tells me either -2 or +2. How do I know that it's -2? Picture. Right, I can see from the picture that the lower bound that I'm interested in is negative, and that's why it has to be -2. Everybody on board? Likewise for the +2, same two curves, same two equations, but from the picture, when it comes time to look at the upper bound, that upper bound clearly positive. That's why +2. Okay, moving along. let's see, for a given value of x, you can see my range of values of y comes from these 2 points, and playing the usual games. Let's see here, the lower bound's the interesting one. The lower bound, let's see, that point is on that curve, which has that equation. I am looking for a y bound, so I solve for y, and I get x squared. Cool. All right, now then not hard argument for the upper bound. However, let's think it through now the other direction. Just because we can, let's slice the other way. Let's do our y slicing first. Y goes from 0 to 4. Thank you, picture. You're going to hear me say that a lot. Picture's really important for these kinds of questions. This course is unavoidably geometric. The geometry is part of what this course is, right? So you can't get around it, and being able to draw pictures just absolutely indispensable. So, all right. Okay, all right, so then for a given value of y, now I think about my x bounds. Let's talk about just to switch it up, let's talk about the upper bound for x. The upper bound for x comes from that point, which is on that curve, which has that equation. And I tell you what, a lot of students will do at that time like this. A lot of students, not taking the process seriously enough, will mistakenly think, oh, okay, so x squared must be that upper bound. And notice it's not. First of all, that wouldn't make any sense. X is a dummy variable here. Its bound can't depend on itself. That just doesn't make any sense at all, right? So it's a garbage argument. What you have to do, again, always be careful. Think about the process. Remind yourself that what we are looking for here is an upper bound for x. So I need to solve for x in this equation. And whereas in every previous example, the fish just jumped right into the boat, that does not always happen. And certainly in this case, it does not happen. You have to do a little, not much, you have to do a little bit of work here. You got to solve for x. I need x as a function of y, because y is my outside variable. And that's what you get. And again, the picture helps me resolve whether it's positive or negative. Let's take a moment to sit on this. Questions. Everybody see what happened there? Super common mistake. I see a lot of this kind of mistake, and it's tragic because it doesn't make any sense at all, and it gives dramatically wrong answers. Even worse, it's a dramatically bad argument. Okay, so be careful with the process. Don't forget what you're solving for, and don't forget actually to solve for it. Okay. All right. Now, real quick, I want to address the natural question of which one of these do we like better, and therefore which one would we want to use in a practical circumstance, if whatever the situation might be that would have us interested in computing this integral. So I have a pretty significant preference here. I like this one. And I'll tell you why. If we look down at this example here, and how do I compute this inside integral in particular? Well, no problem. That inside integral, you just have to look at the antiderivative of f with respect to x, and who knows? We don't have a formula for f here, so we can't actually do that. But, whatever, antiderivatives, we've got techniques, right? Doesn't seem bad until you realize that you're going to have to plug in to that antiderivative, you're going to have to plug in these bounds. So those bounds are going to be part of your integrand for your outside integral. While you're doing your dy integral, you're doing that single variable integral dy, you're going to have square root of y all over the place. Do y'all remember the horrors of single variable integrals that had square roots in them? They weren't good, right? I mean, you get lucky sometimes, right? But there's a lot of potential for those to be really hard, if not intractable, integrals. So I see, whenever, and this is just a good general rule, by the way, for me, whenever I look at an integral and I see ugliness of any form in the inside bounds, ooh, I don't like it. That gives me the creeps. Yeah? Okay, so I don't like that one. All else being equal, I mean, looking at, let me get off of the red because this is the one I like. This right here, I suppose I don't really like the fact that that's not a constant. But hey, beggars and choosers, they can't all be constants. That would mean everything was a rectangle, right? And if you can't have the bound be a constant, a polynomial, not that bad, right? It really could have been a lot worse. So I think this one's highly desirable compared to the other. Now, what's the takeaway on this, and how can you avoid working out bummer integrals, right? When instead you could have been working out much easier integrals. There is no perfect rule that will always magically give you the right answer. But the way I think about it, and I think this is very helpful, is to think about which variable is a function of the other most naturally. And I look at this and I see, look, it really looks like y is very naturally a function of x. So which of these variables would I rather solve for? Would I rather solve for y? Or would I rather solve for x? I would much rather solve for y. So I'm going to put the y in the position where I would need to solve for it. I am not going to put the x in a position where I would need to solve for it, because I think that makes bad algebra. Does that make sense? So think in terms of what's the input variable, what's the output variable. Try to put the input variable on the outside and the output variable on the inside to the extent that you can. Okay. All right. Nice little takeaway there. Another example. So let's see here. We've got this rectangle. This different triangle. Different triangle now. And again, we can slice this up two different ways. Y'all have seen me do a bunch of these at this point, so I'm just going to point out a good exercise is to think for yourself that this is what you get when you slice with dx on the inside, dy on the outside. Make sure you can do that. Things do get a little weird when I try to do the differentials in the other order. What you're going to notice is that for the values of x between 0 and 1, the upper bound is going to come, for y that is going to come from that point which is on that curve. But for these values of x between 1 and 2, my upper bound is going to come from that point which is on that curve. So I'm going to have two different pieces of algebra here. Let's see here. I'm going to need to solve for y in this equation to get that upper bound for y, and I'm going to need to solve for y in a different equation to get that upper bound for y. So I get two different formulas for my y bounds depending on which values of x I'm looking at. Everybody see that? And so I have to break it up into two integrals. I have to sort of chop it, in other words, I have to chop my domain right there and deal with kind of the green side separately and then deal with the orange side separately. And I don't really see any other options. So now again, we find ourselves in this scenario where clearly one of these two options is better, and I hope this is satisfying. Obviously, we like this one better and not so much on that one. So again, we find ourselves very interested in the question of how can I avoid the bad Or how can I see it coming in advance that I would have two separate integrals to deal with instead of just one, which is clearly undesirable. Rare exceptions to the contrary. But so here's my take on it. Rather than writing them both down, the problem comes from the fact, ultimately, that I was on this curve, and then another bad color choice. I was on this curve, and then I jumped over to this curve. Right, the point that defines my upper bound was on the orange curve, then came over to the purple curve. How'd that happen? How'd that upper bound jump from one curve to the other? Well, it happened because those two curves intersected. And notice that when two curves intersect, they make a corner. And as I was doing my slicing in the x direction, keep in mind all of this is with x on the outside. So as I was going in the x direction, as I was slicing perpendicular to the x axis, I sliced through a corner. So try not to do that. If you slice through a corner, and you can just see it right there from the picture, no algebra necessary, right? If you write down your differentials and then imagine that slicing process perpendicular to that variable, and if that has you slicing through a corner mid-process, pretty much any time you slice through a corner, that means you're going to have to stop the integral you were working on, start a whole new separate integral, with different algebra, because you're going to be using different geometry. So that's my little hack. Try not to slice through corners. Okay, last little thing I'm going to show you about double integrals, and then we're going to move on to triple integrals, and that is sometimes the domain is part of the problem to figure out. So here's a question. Suppose I look at this paraboloid. We've talked about paraboloids in the past, and this plane, and if I look at the volume that's between, the volume that's between that volume is this volume here, like that, and let's compute that volume. Okay. Well, I'm going to view that volume as being the sum of a bunch of French fries, as usual. If I can get this thing to cooperate. Here we go. Here's my French fry, and I could imagine that there's a total bunch of the French fries together that gives me the volume I'm interested in. Volume is pretty clearly height times the area of the base. You can see the height. You can see the height as the difference between these two z coordinates. And then the area of the base, that little area there is the same as that little area there, which is going to be however I broke up the total area to make this French fry in the first place. So height times base gives you volume, and there you go, double integral. Oh wait, what are the bounds? What's my domain? Right, and so here's where the sort of the hard part of this question begins. How do I figure out what this domain is? All right, so here's the observation I'll make. If I want to know this curve, if I want to understand that curve that bounds my domain, that curve, you'll notice, quickly comes from where these two surfaces intersect. Those two surfaces intersect when both equations are satisfied. Yeah? Everybody with me so far? Cool. Now let me show you the landmine that a lot of students step on. Again, very common. I see this all the time. What I'm about to show you is absolute nonsense. Right? So, don't write this down. A lot of students will represent these two surfaces intersecting by saying, well, then I need this to equal to that. I see this all the time, and that's an absolutely nonsensical assertion. no reason to believe that x squared plus y squared should equal to 4x plus, to all that stuff. So I have several fun ways to mock this as an argument. Here's one of them. Here's two different, totally different, forget about it for a second, two totally different equations. 3 equals 3 is a valid equation, and 5 equals 5 is a valid equation. Can I argue that these equations are both true only when 3 equals 5? Nonsense. Immediately, obviously, garbage. Nonsense, right? So it just doesn't work. Various other ways that we could make fun of this, but I think that's good enough. So how do we then represent these points that satisfy both of these equations? And the way I would like to do it is to point out that for any given point in the domain, you can talk about the z-coordinate that comes from this first equation. You can talk about the z-coordinate that comes from the second equation, which is z, of course. And what I'm interested in then, I'm looking for points on this boundary, namely points that are directly below this intersection, and at such points, these two z's need to be equal. I need the green height to equal to the blue height. So I need for that z to equal to that z. That make sense? Okay. So that's you'll notice what I do down here in the rest of this solution. I set the two z's equal to each other. Notice that does require a little bit of algebra solving for that second z. And then this is algebra from there. Everybody happy? All right, so heads up, don't step on that landmine. Again, I've seen it a million times. It always makes me sad. I will point out real quick, notice again, this comes up a fair amount. Notice we have to complete the square twice in order to turn this weird quadratic equation into something recognizable. In this case, it's just a circle, and that's convenient. Okay. All right. Okay, so moving along. Good news. Section 5.3 is super quick. This is the shortest section in the book, I think. I don't know. 1.1 is pretty short, right? But this is a contender. This is a very, very short section. There's several things in the section, and don't forget, you're always responsible to read the whole section. Just while we're on the topic, I'll remind you, pay attention to the content syllabus, right? The content syllabus documents what you are and what you are not responsible for. So, the whole section 5.3 is there, but there's very little that really requires discussion. And so I'm just going to point out this one easy little example rather than give you a general method. Sometimes you want to slice in the other order. Sometimes, for example, a question will come to you as an already iterated integral. No double integral given. Just let's compute this iterated integral. And okay, fine, we can go at this in good faith. How would I compute this integral here? I don't know if y'all have ever tried to compute that antiderivative. If you try, you will fail. It's not that it's hard to do, it's that it can't be done. This antiderivative does not fit in what we call enclosed form, and it's a sophisticated argument as to why that is. But you basically using regular standard functions such as exponentials and logs and polynomials and stuff like that. There is no formula that will describe this antiderivative. Okay, so dead end. So we're going to try to switch the order. We're going to try to do these differentials in the opposite order. And here's the big idea. The way you switch the order, again, you cannot do this. You cannot just do the switcheroo, right? Just move the inside to the outside and the outside to the inside. It does not. I mean, try it. It would give you something that makes no sense at all. It would give you meaningless garbage. Right? What we need to do is reverse engineer what is the domain that gave rise to these bounds in the first place. And the good news, this is a matter of reading straight off of the integral. You can see right here it says y goes from 0 to 1. All right, well, there's y equals 0 and there's y equals 1. So my domain must be between those lines. Let's write it down. All right. And then, for a given value of y, somewhere between 0 and 1, question comes up, what formula gives me my lower bound for x as a function of y, right? I mean, if I write x as my inside variable, this formula is telling me how that x bound depends on y. It is telling me x is a function of y. So the formula apparently is x is y. And that's an easy picture to draw. And likewise, my upper bound for x, apparently, x as a function of y is just 1 for the upper bound. And that, again, is an easy picture to draw. X equals 1. So, putting these pieces together, now again, a reminder, let's see here, we already agreed y was between 0 and 1. So between these green lines and also between, for blue on the low side and orange on the high side, and that pretty immediately gives us that this is our domain. So we have reverse engineered the domain itself for the double integral, and thus we can rewrite the integral that we were given now as that double integral. That's the first step in the process. We're not done yet. We do need to sort of slice it up the other way. But does everybody see how I got this domain? Okay. All right. Okay. Okay, so now, phooey on that original iterated integral, we've got the original double integral. And now let's slice it in the other order. X pretty clearly goes from 0 to 1. Let's see here now then, for a given value of x, let's say for that value of x, the lower bound is going to come from that curve, y equals 0, and the upper bound for y is going to come from that curve, y equals x. And we have ourselves now a new iterated integral. Now, okay. Let's acknowledge we started this with an iterated integral, and now, which we couldn't compute, and now we've turned it into a different iterated integral. It's not immediately clear we've gained anything, but the way the cookie crumbles on this one is this is actually a really easy inside integral, not least because x being constant makes e to the x squared constant. That makes this a really easy integral. Antiderivative, you plug in the bounds, etc. Okay, but here we are again facing an x integral, and there's an e to the x squared in there. Again, we're worried that might make this intractable, but notice, very, 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 very importantly and valuably, we have this extra factor sitting in there. Kind of the residue left over from the fact that we already did the y integral, and this integral easily computed. So it's a really clever little method. This is the classic first example to show the value of this method, and so be on the lookout every so often. This is just exactly that one tool that you need, without which you can't proceed. Okay. So that's section 5.3. On to 5.4. Triple integrals. I'm going to go as fast as I can through these sort of formational ideas for triple integrals. Reminder with double integrals. The whole point to double integrals, in fact, I have the little diagram right here. The whole point to double integrals was that it was a way that I could take two-dimensional problems, stuff that's distributed over two-dimensional regions, or that I think about in terms of two-dimensional regions, volume sitting over a two-dimensional region, whatever the case may be, and chop up the two-dimensional region into little pieces and add up all the pieces over the two-dimensional region. Right? So what we're going to consider now is, well, what if I have a three-dimensional region? So, for example, this is my favorite metaphor, I guess, for why we need triple integrals. I like to think about mass, because it's visceral, it's physically relatable, right? So if I have a three-dimensional thing, and I want to compute the mass in that three-dimensional thing, and if the density depends on three, you'll notice, three different variables, double integral just doesn't cut it. I can't view this as distributed over an area. It's not. It's distributed over an entire volume. And there's many other examples that you could imagine. I throw probability in here just as just to keep things weird, right? I mean, there's bazillions of different things that you can argue the whole is the sum of the parts, and that can be thought of as distributed over three-dimensional regions. So we just need to take our idea of a double integral and copycat now to a three-dimensional situation. So here's my three-dimensional rectangular box. We'll get to non-rectangular later, but there's my three-dimensional box. I can imagine chopping that into a bunch of little pieces. How would I describe those pieces? Well, I've already talked about chopping up the x-axis. I've already talked about chopping up the y-axis. We already have those formulas. We're just going to need to chop up the z-axis, following the same patterns. We just get those formulas right there. Notice they look morally equivalent to what we did on the x-axis and the y-axis. And frankly, all of that is just kind of details. That's just formalizing what we mean by take this box and dice it, cooking-wise, right? Chop it in all three different directions, right? And that gives us a bunch of little tiny little, sub-boxes. Right? And then the actual integration argument is just, again, the whole is the sum of the parts. If I want to compute, let's see here, get this all on the page at the same time. There we go. If I want to compute the grand total amount of mass in this whole thing, okay, well, yeah, fine. I'm just going to look one little piece at a time. On each little piece, mass per unit volume times volume, isn't it? Right? And then I'm going to have to add up now. I'm going to add up over the entire rectangular box, slicing in all three directions. So you'll notice I have to add up now in three different directions. So I have three different indices. Yeah, sure. Right? But still, you're just adding up a bunch of little pieces to argue that the whole is the sum of the parts. It's morally equivalent to the idea of a double integral. Is everybody okay? Okay, so this is what we call a triple integral. And I steal the notation and I steal the terminology, right? dV, because this represents volume now. So copycatting the motivation for the notation. Three integral symbols because, well, we're adding up in three different directions. Okay. All right. Okay. So we have motivated the definition of a triple integral. The definition is it's this Riemann sum, and again, a lot of little details, a lot of scary little formulas and indices, and a lot of hairiness in the specifics of the definition. The big idea is that the whole is the sum of the parts. We're chopping it up and then adding it up. All right, now again, for sort of mathematician reasons, good mathematician reasons, the book talks about irregular partitions and arbitrary test points, and again, there's good reasons to want to do this. It's also, however, true that for what we're interested in, namely if the integrand is continuous, these don't make any difference at all, and it's a little bit of an overstatement to say there's just no motivation to do it at all, but certainly it's not anything that we need to be interested in ourselves, so we're not going to worry about all that stuff, so you are absolved of any responsibility for that stuff. Those generalizations that the book does. Okay, so here we go. First example of how to address a application question with a triple integral. As on the previous page, how do I add up all the mass if density is a function of all three variables? Well, the whole is the sum of the parts. There's that shorthand. Right? Whole is the sum of the parts. And then on each little piece, mass is mass per unit volume times volume. Again, that's what mass per unit volume means. Mass per unit volume is what you multiply by volume to get mass. Everybody happy? Okay. All right, now a quick warning. Something you got to be very, very careful with when you're thinking about triple integrals. And this is real easy to mess up. Seen it a million times. Everyone's favorite way to think about single variable integrals when they're in a single variable calculus class is area under a curve. Everyone's first favorite way to think about double integrals in a multivariable calculus class is to think about volume under a surface. And again, these have their moments. They have their, I'm sure it's kind of nice to be able to see a picture, but y'all will recall I've been pushing other points of view, right? I like the fact that a single variable integral can be understood with a single dimensional picture. And I like to think about not, height, but density. I like to think not area, but mass, because if nothing else, this blue sort of single-dimensional point of view on a single variable integral pushes the idea that we're adding up little pieces of stuff, right? It's more generalizable. So I like this point of view, and then likewise, I like this two-dimensional point of view on double integrals. They're both equally valid, so fine, right? Here's the problem, and you can already see it, and the notes give away the problem. If you insist, and I'm going to do this in red, if you insist on this point of view for single variable integrals and this point of view for double integrals, well, you've set yourself up now for a pattern where what was a two-dimensional picture and then a three-dimensional picture is now going to be requiring a four-dimensional picture, and that is not on the table. You can't do it. I don't believe you. If you think you can, I'm not buying it. Right? It's just too hard. I certainly can't. Right? Whereas, if you instead were to think about single variable integrals this way, notice one-dimensional picture. Double integrals this way, notice two-dimensional picture. Then you have a perfectly sustainable pattern leading you to understanding triple integrals with a merely three-dimensional picture. And yeah, it's hard to visualize a little bit, and two-dimensional paper, you have to use your imagination, etc. But it's doable, right? It's a reasonable process. So at a minimum, you need to make sure that you can think about these prior integrals in this way, without graphs, fooey on graphs. Right? Forget about graphs. We need to think about integrals from this sort of, mass point of view, so that you can have a point of view that extends analogously to understanding triple integrals. You just got to do it. Right? And I'll point out another danger, potential problem, is some students say, all right, you know what I'm going to do? Look, I'm sorry, I really like these points of view, and so I'm going to do, this is going to be how I'm going to understand integrals. I'm going to understand triple integrals. Okay, I guess I don't have a choice in that one, but this is how I want to do it. And then here's the confusion that happens all the time, is students will see a three-dimensional thing and then not understand whether is this a double integral or is this a triple integral. So I'm not saying you can't do it this way. I'm saying that it's dangerous because there's significant potential confusion. And again, I've seen that happen lots of times. Right? So anyway, you've been warned. Right? So think of it however you will, I suppose. Okay, and look at that. Perfect timing. We call it a day right there. And y'all have a good rest of your Monday. See you tomorrow. Have a good one.